All right, how are you doing today? And so I'm looking at section 11.2 in the text. So in chapter 10, we saw how we could use ODE 45 to solve a series of couple first order initial value ordinary differential equations. And so now here in chapter 11, what we want to look at is solving second and higher order ordinary differential equations. And so the issue is ODE 45 can only handle first order initial value ODEs. So when we have a second or higher order ODE, the trick to be able to use ODE 45 to solve it numerically is to take your higher order differential equation and transform it into a series of coupled first order initial value ODEs. And so in this chapter, we try and look at hopefully what's a more common example from your physics class, Newtonian motion. So we'll look at descent of a projectile, and then we'll look at projectile launch, say from a cannon. Okay, and so if I'm looking at, say, dropping an object from a stationary point, okay, and so if we model descent in vacuum, then the governing differential equation is d squared z dt squared is equal to a. So essentially, if I have a ball that I'm dropping from some platform up in space, what I know about the ball, besides its initial position, its initial altitude, and its initial velocity, 0, what I additionally know is the only force acting on that object is the force due to gravity. And again, in this first case, we're assuming descent in vacuum. We'll add air resistance later on. So the question is, if the only thing I know about the object is the force acting on it or acceleration via Newton's second law, how can I relate that to tracking its position as a function of time? So the trick is to take my second order ODE and rewrite it as a system of first order ODEs by introducing an intermediate variable. In this case, the intermediate variable is velocity, where velocity is the first derivative of position, and then acceleration becomes the first derivative of velocity. So now what I have is a system of coupled first order ODEs that I can solve numerically, just like we saw in the last chapter. Okay, and so I'll go over to Matlab now, and we'll play around with setting this up and solving, and we'll go through essentially the exercises of this chapter of having fun solving the problem. Okay, so I'm going to go over to Matlab. Okay, and so if I want to solve this differential equation, okay, the first thing I know I'm going to need to create is a rate function. So I'll do new script. Okay, so I'll start with my signature function. Res is equal to, we can call this freefall rate. And our rate function is going to have two inputs. Okay, remember, a rate function will have a single output and then two inputs. In this case, t, and then I'll have my second argument. I'll call it w, where w is going to be a vector of our functions at that time. Okay, and so if I start by unpack, so unpacking w. Okay. So w, the two functions we're trying to solve for in this case are position z and velocity. So we're free to choose them in any order we want, but once we choose that order, we need to be consistent. So I'm going to go ahead and let's say, let's call z the first element. So we'll assign the first element of w to z, and we'll call velocity the second component. Okay, so we'll unpack. In terms of parameters, well, we could put gravity in here, and we'll tweak up the acceleration maybe later. And so in terms of constants, we have g, which is 9.8, and that's our acceleration due to gravity in meters per second squared. Okay. Next we'll compute our rates. Okay, so in this case, dz dt, okay, so the first derivative of position with respect to time, this one's easy, it's just velocity v. Then dv dt, first derivative of velocity is just our acceleration, which in this case is negative g. Okay. Then we finish by packing up our rates. So if we pack up our rates, so res will be dz dt semicolon, because our rates need to be packed up into a column vector, dv dt. Okay, cool. So I'm going to save this as freefall rate. Okay, excellent. And then basic call, if I want to solve it in my command window, would be ODE45, function handle for my rate function. So this would be freefall rate. And to give it a time interval that we're going to solve for. And so in the example in that section, it's solved for 30 seconds. And then in terms of initial conditions, initial z would be our initial height. And in the text, we start with 4,000 meters, and our initial velocity is 0. So initially it's stationary. So if I just call ODE45 in this fashion, okay, default behavior will be to generate a plot. Okay, cool. Okay, so the plot is good. One challenge here, though, is it's going to attempt to plot position and velocity in the same plot window. Okay, and so it's going to be a little hard to see what's going on. Okay. So the first improvement I'll do is, well, okay, so if I close this, okay, so one thing that we could do is if we were to say restore the results to variables, okay, I could just copy this. Okay, so if I store the results to variables, the default behavior is not going to be to generate a plot, just to store the results to variables. If I want to break up M, okay, so so M is going to be a matrix again, where first column will be our first function, second column, in this case, will be our second function, and the rows will correspond to the corresponding times in t. Okay, so if I break up M, so Z will be equal to all rows first column of M. V will be all rows second column, right? And then this can help me facilitate plotting. So maybe a first figure window. I can go ahead and I can plot position versus time. I can do that as, say, a black line. Okay. Let me just try and shrink or get this adjusted a little bit. All right, and I can go add labels if I wanted to. Okay, but in the interest of time, I won't for now. And if I wanted another figure window, I could go ahead and I could plot velocity. Okay, so in the second figure window, I could plot t versus v. Okay, so it looks like my velocity is decreasing linearly, as we expect, since if I look at my governing differential equation, dv dt is just negative g, where g is a constant. Right, so my velocity is going to be changing linearly. And then dz dt is first derivative of this linear expression, so expect it to be second order, right? And so I get this parabolic trajectory for descent. Okay. The one thing you'll notice is if I go back to figure 2 or figure 1, right, and I were say to turn the grid on, okay. So if I look at z of 0, this corresponds to ground. I see that I'm actually getting altitudes less than 0. And so what that would correspond to is, my projectile or my skydiver is tunneling through Earth. All right, and so one of the difficulties with ODE45 is I need to give it this time range. Okay, and oftentimes a priori you don't know what that final time should be. Okay, and so what we'll do next is we'll go ahead and we'll build up our code so that we, instead of specifying this t, we stop integrating when we hit the ground, which is more of the physical scenario. Okay, so let's do this. So the first thing I'm going to do is I'm going to start to build this up. Okay, so let me, instead of calling this freefall, I'm going to save a copy as just freefall instead of freefall rate. So I'm going to start with the function freefall. Okay, and freefall is going to take no inputs. Okay, let me close close this. And I'm going to start by just copying and pasting exactly what we just did in the command window. Okay, so we'll solve our ODE. Okay. We'll break up M into components, I'll call it. Okay, and for now, well, let's add the plot. Let's add, we'll open up first figure window. Just type in figure 1, and figure 1 will plot t comma z. Okay. We'll just type grid on so we can confirm that z equals 0 line. And in figure 2, we'll plot t versus v. And we'll also plot that as a black line. Okay, cool. So let me clear my variables. Clear that. Now if I just run Freefall, okay, it's figure 1, figure 2, all right, they look exactly like we had before, all right. Oop. So things are looking good. All right, so now let's build off of Freefall. And so our issue here is we just arbitrarily choose a time, okay, but again, just running to generate the plots. It looks like we hit the ground before 30 seconds, or we hit the ground before 30 seconds. I don't know, somewhere around maybe 27 seconds. And so what I'd like to do is get our code set up so that it stops integrating at this physical stopping point, right? Don't integrate past the time when you hit Earth, okay? And so let's try and do that, okay? And so the first version of my code, okay, let me put comments on this for now, okay, in case we want it later. Okay. All right, let's update this code so that Freefall has an input of time, and then I'm going to integrate from 0 to t. Okay, cool. And what I'm going to return is res is equal to m. So I want the last row. Actually, let's just break it up. So if I unpack just like we had before, let's return back the last element of z. Okay. So now if I were to call, let's see, so this would be x final would be Freefall, and I've given it a value of 30, right? So after 30 seconds, my x position or my z position is negative 410, right? And so what we want to do is we want to get our solver to stop when z final is equal to 0, okay? And so this is set up now so that I have a function, all right, that has a single input variable and returns a single value back, all right? So and not only that, what we're actually looking for is when the single variable that's being returned back, the time for when it's equal to 0, right? And so this should hopefully just be screaming F0. So if I want to solve for the time of impact, okay, I can use F0, and that'd be at Freefall. Okay, so if I want to give it a bracket, I need to start at some value greater than 0. Okay, otherwise I would have an ODE 45 call from 0 to 0, which would flag an error. Then in terms of an upper bound, well, 30 is beyond when I hit the ground, so let's just use 30. Okay, so doing so, we find that we have an impact time of 28.5714 seconds. Okay, cool. All right, let's get this integrated in our code, and then let's also have it generate our plot. Okay, So this is actually more like freefall air. Okay, so I'm going to have this new top function, res is equal to freefall with no inputs. Okay, and so then what's freefall going to do? Well, we can solve for the time of impact. Okay, so if I solve for the time of impact, T impact is F0, and we'll do at, now this is called freefall air. We search from 0.1 to 30. Okay, cool. So let's save this. So now if I just call a T impact, it's free fall. Oh, it's because I need to call this res. All right, call T impact. Okay, so trying again. T impact is 28.5714. Same thing. Great. Okay, that's excellent. All right. So then, what would I do if I wanted to plot my new trajectory and maybe even return my values of z and v? Well, one way would be, if I call this T impact, I can now solve my ODE for this new final time. Okay, so this would be, or now instead of T, this would become T impact. And let me just copy this and modify it. So we could break them up M into its components. Generate those plots. Okay. If I were to make it so I had all the data returned back, like I had just solved this, my command window, I could return back t, z, and v if I wanted to, right? My final vector of times, positions, and velocities, right? And we'll also plot them right in here for convenience. Okay. Since I moved it, let's delete these. Okay, so let's delete those, and then let's also just delete v since it's not actually used there. Okay, so let's run this guy. Okay, so tzv is just equal to freefall. Okay. Oh, let me go ahead and suppress the output. So if I press return, right, I'm going to get two figures. Okay. This first one with the grids, figure 1, this is our position. Where notice now our position starts at 4,000 and it ends perfectly at an altitude of 0. Great. Right? And even here in my command window, if I was to type z end, since I returned z back, right, essentially it's 0. Negative 5.4 times 10 to the negative 13. Right? And then our velocity would end at that same final time that we didn't know ahead of time. All right, so here I don't know the time ahead of time, but I could solve for it. All right, so that's cool. So I have this function up top with no inputs. Its goal is to first solve for the time of impact, and then once I have the time of impact, resolve my diffie-q over that new time range, and then return back the output from ODE 45. Okay, cool. So that works, and that's good. But of course, we could do better, I suppose, right? So in this chapter, we learned about nesting functions. Okay, so I'm going to create another version called freefall nest. Okay. All right. So when I have this F0 call here, what I can think of it as, one way to think of it in a very crude sense is what Matlab's going to do with F0 is it's going to keep calling this air function with different values of t until this error function returns a value of 0. Okay? The last time it calls my error function should be at the, where I found my solution, where that function is equal to 0. Right? And so in theory, if I just, evaluated my error function at that time of impact, there's really no reason to do it again like I did here. Okay, and so how we can achieve that is using a nested function. Okay, and so what that would look like is, okay, let me see, I should be able to make this full screen. Okay, let me maximize this. Okay, so right now I have this top function, Freefall nest, my error function used by F0, and then my rate function. I would say that they are all parallel to each other. Okay, so they're all parallel. So when F0 calls freefall error, right, this freefall error has its own workspace. When freefall error calls my rate function, it has its own workspace as well. Okay, so what we do when we nest is I'm going to delete that end. And I'm going to add it after freefall error and then tab it in. Okay, so now freefall error is nested in my top function. So what that means is that my top function can see the workspace of my nested function. The nested function can see the workspace of the top function. Okay, cool. Okay, so if I think back to what we were just saying about F0, F0 is going to keep calling my error function until it finds when my error function evaluates to 0 or returns a value of 0. Okay, and so that would correspond to our solution. And so if it found that the last iteration, there's really no reason to repeat the calculation. So what I can do is I can delete my ODE 45 call, and actually I could even delete the Z because I break it up down here. Okay, and so actually let me put V back down here just for completeness, just so they're together. Okay, so the way this will work is, a couple things to point out is these variables are now colored in cyan. If I hover over them, what it tells me is that the scope of those variables span multiple functions. Okay, and so what you can think of that is those are variables that are shared or mutual between a parent function or an outer function and a nested function. Okay, so TZ and V. All right, so we use them up here in the top function. They also exist down here in this nested function, and they're essentially one and the same. And so what will happen here is, I call this top function, and then it's going to go through the lines of command in order. So the first thing it'll see is this F0 call, and it'll keep calling my error function with different values of t until my error function evaluates to 0. At which point it says success, right? Gives you that final value of t and moves on. Okay, and so that last value, time we evaluated F0, actually corresponds to our solution. Okay, so every time I call F0, or every time F0 calls my error function, I solve my differential equation out to t. Final call is going to be with our final time, our solution. And then here within that nested function, I break up m into z and v. So then up here, after my F0 call, if I just move on to generating plots, what it will use for t, z, and v will be those final values from that last call to my error function. Okay, cool. Okay, my rate function I left as it was, and so nothing changes there in terms of scope, right? It has its own workspace. Okay, so let me click restore to bring that back. So now if I call freefall nest, okay, I'll bring up this command. So there's freefall, but now I'm going to call freefall nest. Right? Result is essentially exactly the same. All right, and if I was to call zn down here, right, I get this negative 5.4 times 10 to the negative 13, exactly the same. Okay, cool. Yeah, and for now, I suppose that's enough playing with Freefall.